Hello students, welcome to EPG Pathshala. I am Dr. Amarjit Singh from Himachal Pradesh University, Shimla. Today we are going to discuss about a module uh, regarding inelastic scattering of X-rays with matter from paper Solid State Physics. So the students, let us see what we are going to learn in this module. So that's about defining our objectives. So first of all, we will understand the electromagnetic spectrum and a window of X-rays in entire spectrum, a typical wavelength, frequency, energy associated with the X-ray photons. As you know that there is a wide range of electromagnetic spectrum. So the question is, in which range X-ray falls and what is so important about its wavelength and energy to probe to work as a probe in the material. And the next objective is we will learn a little about the production of X-rays, various excitation processes in materials through interaction of photons with matter. And we will learn about X-ray absorption processes and how we define it in terms of linear absorption coefficients. Now all these processes are finally have developed into some well-known techniques, experimental techniques, and these techniques are used for identifying, for understanding their chemical nature, and say some of the techniques are like XANES, EXAFS, X-ray fluorescence spectroscopy. So we will differentiate between that. So these are the learning objectives of this module. So let me introduce to you a little about X-rays. So William Conrad Roentgen discovered X-ray at the University of Würzburg in 1895. In the 20th century, X-rays have played an important role in gaining an understanding of matter on atomic scale and their quantum phenomena. The discovery of X-rays unfolded a new era of science. One of the major accomplishments was the exploration of the microscopic structure details of molecules, liquids, and solids at length scale of interatomic distances. X-rays can penetrate thick objects that are opaque to visible light. For example, if let us say you are talking about some things which are opaque, the light cannot pass through some materials, but X-ray are highly energetic. For example, metals, they can penetrate to some depth, some micron depth, which is not possible for the light. So now with the help of diagram, we illustrate the range of frequency, energy, and wavelength the X-ray possess in the diagrams in the slides which is to come. So one of the on the basis of penetrating power and applications, the X-rays are usually categorized as soft X-rays and hard X-rays. On the basis of this property, atomic resolution, three-dimensional real space imaging methods are used to obtain the invisible interior structure of the objects. So I talked about soft X-rays and hard X-rays. Basically, these two terms are used to these are used to represent the energies of the X-rays. When wavelength of X-rays is of the order of 1 angstrom, so that has it's a 9 keV energy. So that's hard X-rays, and when the wavelength is up to 5 angstrom or so, so that is a kind of weak energy, and that is called as soft X-rays. So this hard X-rays and soft X-rays both have different purpose, and they are used as a probe to determine different things in solid materials. So several X-ray imaging techniques have been developed for this purpose. For example, real space X-ray microscopy is similar to visible light microscope, except that the traditional refractive lenses are replaced by X-ray lenses such as zone plates. I mean, in optics, you see that in laboratory when you go, you can see that you can work with the lenses, but for the X-rays, such lenses does not work, just because, as we just discussed now, that they have high penetrating power. Instead of reflecting, they usually penetrate. Of course, at certain very low angle, they reflect, but then we need a very large lenses. So zone plates are instead used for lensing system in X-rays. So lensless imaging. Now the next phase is lensless imaging. Get rid of the lenses altogether, and instead a reciprocal space coherent diffraction pattern are recorded. So we record the pattern in reciprocal space, and then they are subsequently inverted using computational algorithm to obtain a real space image. So idea is that you obtain the picture in a reciprocal space, and then you Fourier transform to get the information in real space. So that's called lensless imaging. You are not using lenses in this. So these kind of techniques are nowadays available, and they are being used at the synchrotron radiation techniques. So these techniques allow the recording of high resolution images that can be sensitive to elemental composition, chemical state, the state of magnetism, etc. Discovery of X-rays. So here you see that on the right hand side, this is a picture of Professor William Conrad Roentgen, who discovered X-rays. X-ray became so popular and interesting tool in medical field, and nowadays they are very much used in determining the structure of material at atomic level. In this slide, you see an electromagnetic spectrum, and here you see that there is a region of IR, which is infrared, visible, and UV, ultra UV, and soft X-rays and hard X-rays. So when we go from left to right, the wavelength which is decreasing, and this is the frequency which is increasing, and also the energy here. This tells us that when we are talking about X-ray, what is the wavelength and energy we are dealing with. So when we are talking about X-rays, so this is wavelength is near 1 angstrom, or energy somewhere between 1 kilovolt to 10 kilovolt, and wavelength between 1 and 10 angstrom to 1 angstrom. So this is the limit we are working with X-rays. The idea of discussing the wavelength is this, that we can probe the same scale as that of wavelength. So when we have wavelength as small as angstrom, basically we can probe the structure of as small as angstrom in material science. This slide shows an interaction of X-rays with matter. So as you can see that when X-ray goes and hits some material, there can be several processes which would result, like pair production. This is one of the possible outcome of this interaction. Then there can be a photoelectric absorption. It means the photon will be absorbed, it will emit an electron. There can be a scattering, there can be Compton scattering, in which the photon loses its part of its energy, and in simple Thomson scattering, it may not lose, it can just simply scatter. And there can be some other processes like fluorescence and Auger electrons. So when a photon of X-ray is interacting with the material, so these are the possible things which can happen, or possible interactions of X-ray with the matter can happen. So this slide shows especially about photoelectric absorption. This is pictorially demonstrated. In atoms, we know that there are K, L, M shells, and there is a continuum. Continuum here means that as you go above in the energy difference between the cells becomes smaller and smaller, so they becomes almost continuous band of energy. So this shows that the energy of the photon is so much that it removes an electron from the K shell and put it into the continuum. It means outside the atom. Now it is no more bonded to atom, it's a free electron basically. So that is what about is photoelectric absorption. So in this slide, we have shown what is fluorescent X-ray emission. As you have seen in the earlier process in the case of photoelectric absorption, that one atom was removed from the K shell as it is visible in the left hand side of diagram. Then what happens is this atom is unstable because first the lower energy shell should be filled and then it goes to higher energy levels. So definitely when lower energy level is empty, the electron from some above energy level will jump to the lower level, so that the atoms which was excited now becomes de-excited. So in this process, when atoms become de-excited and obtains its ground state, then another a photon of the energy, which is the difference between L and K shell, will be ejected. Now you can see that in this process there can be transfer of electrons from L shell, and from higher. So depending on that, there will be an energy of this fluorescent radiation, and you can understand that the energy of this fluorescent radiation has to be smaller than the incident X-ray source, because incident X-ray source is comes and it take out the highly strongly bound electron from the K shell, and another electron which is jumping to fill up this is basically also a bound electron in higher orbit. So naturally it does not possess as high energy as that of photon, which removes an electron from the K shell. So this slide illustrates Auger electron emission. So now as we have seen in the last process in the case of photoelectric emission, that an electron was emitted from K shell, and now when the atom is de-excited to one of the electron from the higher level, say L, will come to K, and then as a result of this de-excitation, instead of emission of a photon, just like as it was in case of fluorescence, rather an electron is emitted. So here in the process of de-excitation, in place of photon, an electron is emitted from a higher cell. So that is Auger electron emission. So basically in fluorescence emission and Auger electron emission, these are two de-excitation processes. In fluorescence, it is the photon which is emitting, and in Auger electron emission, it is the electron which takes up this energy and is emitted out of the cell. In this slide, we will define an important parameter called linear absorption coefficient. Now you can see in this diagram that this is a slab of thickness x, which is basically any given material, and X-rays are incident on it from the left. So we can see here again there can be several processes like scattered X-rays, fluorescence X-rays, photoelectron, and transmitted X-rays. So in this process, that some of the X-rays or a portion of this intensity is absorbed, and only this partially we can see that there are some intensity or X-rays which is coming out to the sample which remains unabsorbed. So when they are getting absorbed, they are giving rise to several processes. So this absorption of X-rays has been combined in a coefficient called linear absorption coefficient, which is shown here below. So this equation says that I naught, this is the incident intensity, and I, this is the intensity after absorption, and mu, say this is the coefficient which we do not know and right now, and x is the thickness of the slab. So here it is assumed that this x here is the thickness which have an infinite slabs in this, and there comes this exponential relation. So basically the idea is this, that from this equation we can find out linear absorption coefficient if we know the thickness of the specimen, if we know the incident intensity, and if we know the intensity after absorption. Or in other way around, if we know the absorption coefficient of a material, we can calculate that what would be the intensity from a given material, from a thickness of a given material after absorption. Okay, so now let us mathematically formulate how to calculate this linear absorption coefficient. So you can see that when a given intensity is incident on a specific sample or specimen, and you record the transmitted intensity on the other side. So first of all, your sample should be so thin so that some of intensity is transmitted. If you use very thick samples, it is not possible to get the transmitted intensity, so the information will be lost. So we need such a thin sample which has some given thickness, let us say z, so that you can measure the intensity on the other side. Now question is, on the intensity, the absorption is proportional to what? So first of all, it is proportional to the atomic density present in the specimen, because the larger the number of atoms, or densely packed the number of atoms in a material, the more will be the probability of interaction and absorption. And definitely absorption coefficient. So absorption coefficient is a property of given atom. So some of the atom, as you see, they absorb more radiation, other atoms absorb less. So it also depends what species it is, what kind of atom it is, and of course on the thickness of the specimen, because larger the thickness, you can see that the intensity will get more and more chance, this beam will get more and more chance to interact and get reduced in size. So this formula W is equal to I rho at dz omega a, this equation represents that what is the probability factor, what is the probability of an absorption of a given incident radiation. Here in this slide we have shown this mathematical form of this linear absorption coefficient. As you can see that this is product of atomic density and absorption cross section. So this subscript A here and AT, this represent atom. So this absorption cross section is dependent on what kind of atoms we are using. For example, sodium, chlorine, hydrogen, or any other atom which will have different absorption cross section. So this is further uh, extended, this formula, into the real density, Avogadro number, molar mass, to relate this linear absorption coefficient. And when you have several different kinds of atom in a given material, so this lower relation sum over J is any particular type of species or atom we are using. So from there one can calculate the linear absorption coefficient. In this slide, this diagram shows that how absorption cross section sigma, this depends on the energy of the incident radiation. When you have an X-rays, so if you change the energy, as you can see from left to right, this absorption cross section is linear and it drops, and then you see the sudden edge, it rise. The sudden edge demonstrate that from now you have gone on to the different energy level. This has occurred due to the emission of electron from higher energy shells. So this kind of edges you will see further if you extend this spectra, and this edges reflect that now we have gone into a different shell. The shell which we are talking here is KLMN, which are discrete energy shell. So edge here basically represents switching over, when we switch over from one shell to another shell. Experimental measurement of X-ray absorption edge. So here you see in the slide we have shown a diagram on the left hand side where a monochromatic X-ray beam is incident on the sample. So monochromatic means it has a single wavelength, it's a given wavelength, and we measure the intensity of this one using an ionization chamber. So I naught is an incident intensity, and then after it passes through the sample we again measure the intensity, so which is the transmitted intensity, again in ionic chamber, and on top you can see that this IF, fluorescence detector. So this is a detector which determines the energy of the emitted radiation. So how to measure the absorption edge, or we can say the different fluorescent, the energy of the different fluorescent waves emitted from the sample. Here our monochromatic beam is working, is a source of excitation, it excites the sample, then there comes a fluorescence radiation with a wavelengths, with a different wavelengths of a smaller energy. And this diagram on the right hand side shows how this transition takes place. Now you can see that there is a K shell, which is the ground shell, the lower cell in this diagram, and then L, and L is, you can see that, further divided into some 3 subcells, L1, L2, L3, and M is again divided into 5, and so on. And you can see that the transition from higher energy to lower energy takes place with some certain selection rules. Now with this, each kind of transition which is allowed between higher energy level and lower energy level, they emit, you can see that they can emit a given number of wavelengths, which of course will be less than the wavelength of the incident radiation. So, and using this fluorescence detector we identify which wavelength it is. So basically this technique works as a fingerprinting technique to identify materials, since these lines, these energy levels, are characteristics of a given material. Therefore the edge or the particular lines emitted work as a fingerprint for that material, and it's very easy then to identify the given material. We have slightly elaborated what we have seen on last slide. Here we divide this shells or subshells, as you can see that it is in S and P orbitals, and that's the total angular momentum as a superscript and subscript as a spin angular momentum. And now the transition is shown, that is called K line and L1, L2, L3 line. This particular diagram is for platinum, and on the right hand side one can see the spectrum. So to see the spectrum one has to vary this wavelength. Now in the last slide we were talking about a monochromatic source, but this data is not from the monochromatic source, because for changing the wavelength from 0 to 1.5 angstrom you need either undulator synchrotron sources, or there has to be some source which has all these wavelengths. And now we can see, or we can vary this wavelength and see how much absorption is there at a given wavelength. And first, as we go, and there is a little notch at point 1, and this shows K age. So there is a age, and then it again rises up and it shows L1 age, L2 age, and L3 age, and this goes on further. So if you extend it further, it will show you the edges for the M. So this edges mark the energy or the wavelength, and this is a particular of a given atom. So that's how we can chemically identify a given material. Now, as we discussed, for identifying the materials, this absorption age is of very importance. Now, this spectroscopy, which is used to identify the materials, is called X-ray absorption spectroscopy. And this diagram which you see on the right hand side, this is an absorption age, but this is slightly magnified, and you can see that there are wiggles and oscillations. These wiggles and oscillations are characteristics of the energy level of an environment. So this gives a very important information. On top it is written XANES and EXAFS. So this is the classification of this X-ray absorption spectroscopy into two regions. So XANES is X-ray absorption near edge spectroscopy. So here we find out the information of this peak near this edge, and this second is known as EXAFS or extended X-ray absorption fluorescence spectroscopy. So the EXAFS region is sensitive to radial distribution of electron density around absorbing atom and is used for quantitative determination of bond length and coordination number. So it is like if you would like to find out in a given material, let us say sodium atom, and you want to find out what are the nearest neighbors, what is the bonding length, and what is the coordination number. So that you can find out from this EXAFS, and so this proves to be very useful in determining the bond energies and bond length and chemical analysis of the material. So students, let us summarize what we have learned in this module. So first of all, we learned that X-rays are a part of electromagnetic radiation towards the high end of energy spectrum, which has a high penetrating powers in the materials. When X-ray falls on material objects, the atoms of the materials are excited to higher energy state. So when they are excited to high energy state, they are de-excited and they emit radiations or electron. So that way we can have an information of the energy space of that material from the radiation which has come out as a result of excitation. Okay, so as a result of the atoms when de-excite, there are number of processes which happens, like so photoemission is a process in which an electron is ejected and as electron can come out, and you can see that the atom is already excited. Now it can de-excite in a number of ways like fluorescence, Auger electron emission, etc. We also learned that there are some techniques that if you look near the absorption edge, so we have seen that in every energy spectrum there are absorption edges. So if we look at this absorption edges have a structure. They have a structure near the edge and slightly extended edge. So from this wiggles in the edges, we can find out, explore the chemical environment, the bond length, the presence of impurities, etc.